Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my great pleasure to introduce Joe today, that came from Princeton. Josh has been working on the last couple of years on software-defined networks, and he has basically presented a paper at NSDI last year about Pyretic, which is a better way of actually designing SDNs. That paper won the Best Paper Award in the conference, one of the many that Best Paper Community Award, basically Best Paper that gave actually code and data for the community to play with. Josh also, before that, he was at Columbia where he finished his PhD. And during that work, he was involved in a startup that, it's not really a startup as I understand now, it is more of an established company.
It's doing okay. But.
Okay. He has also done a couple of stints at Microsoft Research as an intern. In one of them, he did a paper, Sleepless in Seattle, but unfortunately, he didn't talk about us. He talked about machines. So a lot of us actually are sleepless in Seattle. And yeah, over to you.
Thanks so much for the kind introduction. And thanks, everyone, for coming out. I'm really thrilled to be here today, and I'm excited to tell you about the work that I've been doing on designing controller abstractions for software-defined networks. I've got a lot of material to pack together, so we'll see about the pacing depending on your questions. Maybe we'll skip a little stuff. Maybe I'll elaborate on some points. But before I jump into the talk, let me tell you a little bit about myself. So I like to study network systems. In particular, I'm interested in the way that end hosts, whether those are laptops, servers, mobile robots, what have you, interact and influence the network that they use to communicate and vice versa. So the kind of things that I like to explore in my research and the systems I like to focus on are ones that might take some knowledge of the network, some network communication, and use those to improve the way that end hosts function, how they perform, speed up their storage or access to storage, for example. I like to do things in the opposite way, which is what you're going to be hearing about today, where we take resources provided by the end hosts, whether they're computational or they're wireless radios or some other type of feature they can provide that the in-network hardware really doesn't have access to, and use that to improve and enhance the way the network functions. And also new types of systems where we more tightly integrate the end hosts with the network and are able to do X, Y, or Z faster or better. So today's talk is really going to be focused on how we can use a controller running on end hosts to better utilize, manage, and, well, control our network's data plane. So this is a hard problem. Today's networks are really messes of complexity, as illustrated by the diagram behind me, which shows sort of your typical enterprise network. And the interesting thing about these networks is while more than half of their cost goes to the operations personnel, the network engineers that are managing, configuring, and running these things, more than half of the outages that occur in such networks are because of operator error. So why is this? Well, there are two reasons, at least. But there are two I'm going to talk about today. One is fundamental. We want a lot out of our networks today. There are lots of different interacting components, or at least logic components. You want to provide end-to-end connectivity. You want some traffic moved more quickly than other traffic. Some traffic may need to be blocked. You might need to balance traffic across servers or across links and do all sorts of other things. And this is all in conjunction, in combination with one another. So you need all of these things to combine together and play well, each of which may be changing over time. So you've got this problem of combining lots of different things, and also each of them, and possibly the way in which they're being combined, is going to be changing over time. And then this is exacerbated by sort of a person-made problem, this engineering, what I would say, bad interface for controlling the network. And it's not actually one interface, it's many. So there are over, right now, when I checked before I came here, 70 internet standards for managing network control, along with 186 best practices, hundreds of supplemental, semi-official things, and who knows how many proprietary vendor-introduced mechanisms, Cisco's stuff, Juniper stuff, et cetera. And from all of these different interfaces, network engineers today need to kind of cobble together the network data plane behavior that they desire, that they intend, which makes it no surprise that there's so many errors occurring in this process, and that it's so highly human involved, so manual. So the key idea, in my mind, behind software-defined networking is really, let's go ahead and fix this interface, fix this mess of different ways of controlling the network that all overlap, and instead let our network engineers focus on the truly difficult portions of the problem, which are figuring out how to combine lots of potentially sophisticated functionality that's changing over time. And yeah, let's move on to the next slide. This is what the first generation of SDN really did. We introduced something called Openflow. It came out of academia, Nick McEwen's group at Stanford, and it really has just taken off like wildfire. And essentially what Openflow does is it provides us a single unified way of programming or controlling or managing the data plane functionality of our in-network devices. And this is great because now we can programmatically control the network feasibly for the first time. But it has its shortcomings, which is where my work comes in. So the shortcomings are Openflow's at a fairly low level. So it doesn't really help us with those fundamental problems of combining lots of complex software or sophisticated software and dealing with and expressing the dynamics of those individual components and the way they come together. So my work's really about supporting modularity so we can combine these things and providing abstractions for encoding dynamic controllers. And two different systems, Pyretic, which was already introduced, and a newer system we're working on called Kinetic that deals with the dynamic portion of things. Pyretic's more modularity. The flame splits in half. Maybe, well, I think it's a reasonable icon. Anyway. So the work that I'm going to be telling you about today really has kind of two phases to it. One phase to both of these different projects is one that's an interface. So we're designing an interface upon which programs can be built. The second side is the runtime architecture, that actual computational machinery that sits on the end-host controller and realizes the abstractions presented by the interface and pushes them down to the network's data plane. One brief note over here. Today's talk is, because of time constraints, going to tilt a little bit more to the probably a bit more to the interface end than the runtime end, simply because a lot of the runtime techniques tend to be motivated by concerns in the interface. And, well, we need to understand the interface first for them to really come across. But I'm really happy to talk more after the talk, and I'll try to slip in as much as I can about the runtime. So, OK, our talk outline. What I'm going to be doing is trying to create a better interface. So I'll need to tell you a bit about what the situation is now for managing the network, give you a little more detail into that, and how Openflow changes that picture and where Openflow falls short. Once we've covered that background, we can really jump in to talking about the abstractions in both our interface and our runtime for doing modularity and dynamics. And I'll wrap up, as time allows, with some brief remarks, including a little bit of evaluation. So let's just do sort of very basic networking in case anyone here is from far outside the discipline. If you aren't, you can take a little nap. It starts with end hosts. They need to communicate. So there are going to be a bunch of links and boxes that connect them. So that way they can send each other messages. In this case, these boxes happen to be called Ethernet switches. But the key thing I want you to take away from this slide is that each of these boxes actually has two lives. It has a role as a control plane entity, where it's making decisions about which traffic should flow where, when. And it also has a second life, or a second role, as a data plane entity, actually making sure that packets get forwarded from one link, incoming link, to the next outgoing link or set of outgoing links at the low latency and high throughput that we demand out of our networks. So coming back to our story, our desktops can communicate with one another, but they need to access services on the servers. So those servers are going to need to be connected by their own set of links and boxes. In this case, we call them IP routers. But what I'd like you to point out to you is that these boxes aren't exactly the same in terms of their data plane, but they're very similar. The real difference comes in the control plane, which is completely different. Ethernet switching is very much plug and play, learn where hosts are, over time, add something, pull something out, whereas IP routing is very much more focused on being structured and optimized. So two different control planes, but relatively similar hardware. And this theme is one which is going to repeat itself over and over again. So we want to bridge these two networks that each have their own way of moving packets around and their own control interfaces. So we'll add a new box, a gateway, which is going to run its own stack of logic and have its own set of interfaces to bridge between them. And now that we have traffic moving across this network, we may need to load balance it across our servers. So yet another box that's going to be in the network with its own interface and own control logic. And this continues on. So ISPs come in. So we'll need our interdomain routers. And since traffic from the outside, there are bad people out there, we need our firewall. Of course, there are wireless nodes, more types of boxes. We'll add deep packet inspection, billing, compliance, all sorts of stuff ad absurdum. And we've got a very complex thing to manage at the end of the day. Each one of these boxes has its own set of interfaces. Each one's running some distributed logic. And this is just a nightmare to manage, to control, to set up. Oh, left the ad absurdum off. So this is where Openflow comes in. Openflow really is about decoupling the control plane from the data plane by introducing an open standard interface for having the control plane program the data plane hardware, which lets us move to a world, well, rather from a world in which we have these wildly heterogeneous interfaces for managing and controlling our network's data plane and lots of distributed logic running around, to one in which we program everything using a single unified API. And we can write applications in that single unified interface that then can run wherever, possibly on some logically centralized end hosts. So it turns out that this is quite impactful. It has gone from academia to industry in a short period of time. There are all sorts of groups and organizations and meetings devoted to SDN at this point, along with a whole bunch of controller platforms which are fairly well developed, or at least somewhat mature, all of which are Openflow centric, and I'll explain what I mean by that momentarily. And you've also got companies, very nice companies, some of them, that are developing, deploying, and purchasing this technology and really investing seriously in it and getting good results out. So this is all fantastic, but it's still far from ideal in my opinion. And to explain why, let me show you what's going on inside one of those typical Openflow-centric controllers I was talking about. So in here, you basically have a program that's been written in some standard programming language like C, Java, or Python. And it uses a domain-specific language or an API, basically Openflow, to control the data plane functionality of the network switches. So why is this bad? Well, Openflow is quite low-level, hardware-centric. So it turns out that writing programs in it are going to be, to write programs in it, one is going to need to go through a tedious process of trying to figure out very low-level logic that's fairly unintuitive, at least to humans. And the resulting products are going to be really anti-modular. They're very, very difficult to combine. And I'll show you some examples in a little bit. Moreover, when we get to And that's without any dynamics. When we get to the world of dynamics, we run into a whole other set of concerns, like, well, can I predict the future behavior of this thing that I've written? And will it violate any important properties? So can I verify its behavior? How do I think about structuring it properly? And let's see, what else? Oh yeah, optimization, trying to optimize how it actually installs rules on the data plane. All of these are going to be issues. The one thing that we do get nice is we don't have to spend much time worrying about architecting a runtime. This thing's going to be mostly a shim that just takes the Openflow DSL, the Openflow API used by the program, and just spits it out as Openflow messages on the wire. And I can now be precise about what I mean by a controller platform. That's going to be the combination of an interface and a runtime. So everything below the program on the controller that I've shown you. So let's go a little bit further, dig a little bit deeper, and see how Openflow works, what the models are for interacting and controlling with the network. In the context of this simple example shown behind me, we've got just a single SDN switch on port 1 connected to the internet. Ports 2 and 3 are connected to servers A and B respectively. And there's a control channel, perhaps over TCP, tunneled over the network, or perhaps on a separate control network that goes to our controller host. So by default, packets that come into this network are going to get sent to the controller. That's what the switches do by default. The controller can do any kind of arbitrary processing it wants, produce new packets, and then if it chooses, inject them back into the network. So very powerful model, but it has its costs. Namely, you get a lot of delay, latency increases, because you're processing and you've got this round trip time back and forth. And doing that processing induces significant overhead on the controller. So the second way of interacting with the network is to actually install rules on the data plane. And then our traffic can go through, no additional latency, no overhead on the controller. But this, too, has its trade-offs, its costs. In particular, there's a smaller world of types of analysis matching you can do on the packets and actions in terms of transformations of output that you can do when you're restricted to your data plane hardware. And you've also only got a limited amount of space in that hardware. So we're inherently going to have this trade-off with our controllers over how much interpretation we do versus how much compilation we do. And I'll define those terms later on in the talk more precisely. So how do we control the switch tables? What's this hardware sort of model that's used by Openflow that we're going to be improving? Well, let's look at a simple table in Openflow style. So that's the green box shown behind me. It's got several rules or lines in the table, and each one of these rules is going to have a pattern that matches on packet header bits. So in this case, bits in the source IP field of the packet. It's going to have an associated action with that match, maybe forwarding out a particular port, and a set of priorities. Because one of the key restrictions of these tables is you only get a packet to match one rule in the table at most. So if we have two rules, like say the top rule and the bottommost rule, which could both match a packet destined to IP A, well, the priorities are going to solve it for us. We'll go with highest priority. And also when shown are a bunch of rules for the number of counters and a number of counters. Each rule has one for bytes and the number of packets that have hit that rule since it was installed in the data plane. So how does this program work? Well, if we've got a packet that's going to A, it's going to hit the highest priority rule at top, go out port 2. Likewise, B is going to hit the middle rule, go out port 3. And anything else is going to hit the bottommost rule. So implicitly, we've encoded those packets not matching A and not matching B are going to be forwarded up port 1. And this gives us a very simple IP router, matching on IP field and forwarding packets out. Now, the flexibility and the brilliance of Openflow is very simple interface gives us lots of stuff. We just change the set of bits we're matching on to look at the header bits in the packet that match on MAC address. All of a sudden, we have an Ethernet switch, which is going to match on MAC address and forward out ports. If we want, we can add an additional forwarding action to one of our rules, and now our switch is multicasting. Or we could make a table where some of the rules have no actions whatsoever, implicitly dropping that packet. So we've made a little firewall over here for packets that are coming from host X. Finally, we can sort of combine more sophisticated patterns with one additional action operation, modify, to be able to balance our traffic. Here we're taking traffic destined to C, and we're now going to rename its destination address to either A or B, thus balancing across servers A and B, depending on the source IP prefix. And now we've got our load balancer. So this is a really nice, flexible model for utilizing the hardware that Openflow presents. But can we combine two tables that are made in this way? And I'll show you a first example involving what I call sequential composition. We'd like to have our load balancer first modify the destination address, and then our routing module route based on that modified address, not based on the original. So can we combine these rules? And remember, we only get one match in a table, so as to get the desired functionality. Well, the answer is no. And if that's not immediately obvious, to give you a little intuition, think if we were to put the load balancing rules before the routing rules, well, every packet's going to go through the load balancing rules, match one of them, and either get modified or dropped. But none will ever reach the forwarding rules. So we'll balance without forwarding, and vice versa. Not good. Let's say we want to do parallel composition. So we want to route, and at the same time, we want to do something new, which is, well, just an address that has no actions, a rule in purple that has no actions. But in this case, it's meant to be a stand-in so we can actually have an entry in the table that counts packets. We want to count the number of packets coming from host X. We're going to run into the same problem again. And as a result, if you look at the kind of composition facilities offered by today's controller platforms, you'll actually find they're really kind of flaky. Taken from the POX documentation, not all components work together well, but some do. What you're left to do with that, I'm not quite sure. And this is not just isolated to POX. I've some references below. Feel free to go through the documentation, or I can show you later. Question?
So in your examples, why can't the two tables that are of different colors be treated as different Openflow tables? You still have the restraint of one match per table, but then they would compose, at least in those simple examples.
OK, so that's a great question. And we can go deeper into it later, but I'll give you a quick answer in two parts right now. The first part is because we'd like to be able to implement things as widely as possible. And a lot of the Openflow APIs, or the APIs we have available to the hardware, don't actually show us this kind of multi-table setup that's in the underlying hardware. So that's point one. The second point is you don't know a priori how many different pieces of logic you might want to say sequentially composed. So if you have 3 pieces of logic, and you happen to have 3 stages in your pipeline, and each stage happens to match the order and the header bits that you want to use, then OK, you're great. But if not, you're not. And if you have more things to combine together sequentially, let's say 4 stages, and only a 3-stage pipeline, again, you're sunk. So ideally, we'd like to at least have the machinery available to be able to compose these kind of things together on the same table if needed. So dynamics, won't go into it. I'll let you kind of extrapolate. But things get even harder. We'll see a little more detail later. But I'll just show you a quick snippet of what's a very simple and kind of canonical piece of dynamic logic that runs on those Ethernet switches mentioned before over here, written in POX. So this thing is really quite simple. And the amount of code it takes is a bit daunting. And the level at which the logic is specified, well, you'll need to take my word for it. Or I can walk you through it on the slide afterwards. And actually, of the Openflow controllers I'd mentioned before, POX is probably the most concise example of this particular application. So now that I've finished with the introductory material and the background you need, I'm going to move on and tell you about our modular interface design. So the key to providing a truly modular software-defined network and controller platform, in my opinion, is figuring out how to design an interface that really supports that modularity. And the thing we need to do that is we need to abstract the various features that are present in this hardware model that Openflow exposes and break them up so we can then combine them in a modular fashion instead of the anti-modular fashion of just smashing two tables together and getting nothing that works. So how do we do this? Well, based on an observation that a flow table really is essentially acting like a packet function, a function that's going to take an input packet, a packet at a particular location, which from now on I'll call a located packet or just a packet for short, and is going to output some set of packets, in this case the exact same packet, but just at a different location. And so we can think of every table as just being a function that's going to do transformations. And using, oh, well, before we go there, and this is very precise and abstract. So like, let's say we want to make a function called flood that's going to run on the network shown behind me. So we've got a packet. It's going to arrive at a particular location. Sorry, the animation went a little too quickly. Let's do that over again. Packet arrives at a particular location. We'll evaluate the function based on its current location, get some output. That output's going to get sent across the network. That's what the network does. The links do. They take something in, put it out. We'll evaluate again. This time we get two output packets. They go out. One packet stays within our network. And it turns out this time there are no further links to go. We finished flooding, so we drop. So a very sort of nice, abstract way of expressing what we mean. It can apply to the whole network as opposed to one particular switch. And at the same time, it provides a nice level of abstraction, which, just a side note, so all Pyretic packets actually contain this information in their header. So the programmer has access to sort of virtual headers for import, output, and switch that they can use just like any other header value. So now going to our interface design strategy, what we're going to do is we're going to sort of take the hardware model presented by Openflow, and we're going to abstract the flow table as, well, abstract the features of the flow table as either being functions from packets to sets of packets or operators that take multiple functions and combine them and produce a new function from packets to sets of packets. So let's see how we do this. Well, the first function we have is one which we call filter, and this abstracts the Openflow's matching capabilities. So we have a function, primitive function, match a field equals to a value. Let's say we evaluate that on a particular packet. Well, what we're going to get out is the singleton set containing that identical packet, or a copy of that packet, which is identical, if the packet's field matches the value. And if not, well, we're going to get the empty set out. What about our next one? Well, modifications are going to abstract individual actions. So if we modify a field equal to a value on a packet, we're going to get the same a copy of that packet, which is identical, except for one change. F is now assigned to value v, and that's going to be output, again, as a singleton set. And it turns out this is really nice because we have those virtual headers in our field for location. So what we basically do to do a forward, it's just a special type of modify. Namely, we want to forward out port A. That's just modifying the output field equal to A. OK, special filters. We had before our load balancer, we kind of had this bottom rule, star goes to no actions. And what we really meant there wasn't drop the packet. We meant, hey, pass the packet on unchanged to the next module. Whereas in our firewall, what we really meant was drop. So we provide an identity function, which takes the packet and always produces the singleton set with that exact same packet, and drop on packet, which always produces the empty set. So now we can actually disambiguate between these two cases. So we're more expressive than Openflow. And finally, one last set of primitives before we can move on, queries. So we want to be able to abstract the idea of sending packets to the controller or of counting packets. And you'll notice this is the exact same flow table as the one we were using for firewalling in the purple at the bottom. Source IP equals to X, no actions out. So how do we do this? Well, we provide two query functions, primitives, forward bucket, which is going to take a packet and basically not propagated through the data plane. It's disappeared from the data plane because we're going to be sending that packet conceptually, or information about that packet, to the controller, where it'll be stored in some data structure, which we call a bucket. Likewise, we have count buckets that are going to do the same thing in the data plane, but are going to go to a different type of data structure and send a different type of information to the controller. The difference being forward buckets actually send packets, and the packets are stored by the bucket, while count buckets are going to store aggregates on packets, so counts and bytes. Yeah.
Store and collect other information from the packets, beyond just bytes and packets.
So, well, for example, if you were to take a filter, like let's say you wanted to know the packets that matched some particular source IP, right? You
could I just measure the average packet size?
If you wanted to measure, well, yeah, well, what you could do is to measure the average packet size, you would take a count bucket, and the count bucket's going to give you both the number of packets and the total aggregate size. And then you divide those two numbers, and you've got the average packet size.
If I wanted to get something like application size, to go inside the packet and see the average application size.
Oh, so if you want to do deep packet inspection, then that's not supported on the data plane. The hardware doesn't do it for us. So you'd use a forward bucket and actually get those packets to the controller. And then you'd process them using a variety of libraries, which I can tell you about later, for doing that kind of processing.
Your language actually doesn't support it because it doesn't match the hardware.
Exactly.
The language could support it.
Yeah, the language could do anything, but then compiling it and more importantly, so compiling it becomes more of a challenge, but more importantly, giving the programmer an idea of how expensive this is, it becomes a real challenge. Because now if you use a forward bucket, you're not going to get much overhead except what you do in terms of processing. But if I were to give you this random operation, you'd have no idea like how costly that is. Maybe you'd end up totally hosing your network's performance. So we try to, there's a trade-off here between what we want you to be able to express, which is everything, and what we can efficiently give you or at least tell you how expensive it's going to be. So everything else that's in our table, so there's multiple actions for a particular rule, multiple rules running at the same time at different priorities, and this sort of linkage between matches and actions are all going to be abstracted by basically two simple operators, plus, well, one more. Parallel composition is our first operator, so that corresponds to that parallel composition example I showed you beforehand. And parallel composition is the plus sign. And basically, when I say two functions parallel composed are evaluated on a particular input packet, what I'm saying is exactly the same as saying I'm going to input the first function on that packet, I'm going to input the second function on that packet, and I'm going to take the union of those two outputs. That is parallel composition. And this lets us do two actions just by itself. And if we want to do multiple rules, well, if they don't overlap, it's all we need. If they do overlap, well, then we may need to use some filters with negation to make them not overlap. And I'll show you some concrete examples of that momentarily. So negation was that other operator I mentioned. The other big operator is sequential composition, corresponding to the balanced then forward example I mentioned earlier. And here when we say function A, then function B on a packet, it really means I'm going to apply A to the packet, and then I'm going to apply B to that output. Of course, there's one little mistake here, namely that B takes a packet, not a set of packets, which is what A outputs. So we're going to change up our definition slightly. So we're basically going to unwrap each packet produced by A, then apply B to it. And if they're more than one, take the union of those sets. Sounds good? OK, great. So with this, we've actually completed a total interface redesign, going from this low-level hardware-centric, anti-modular, unintuitive model that Openflow provides to a much more abstract, more expressive, and hopefully intuitive, and definitely completely modular DSL for writing data plane network policy, basically. So let's look at this in some examples. We've got our load balancing example over here in Pyretic. doesn't look all that much dissimilar. There's a correspondence. Each line in the expression in Pyretic corresponds to one of the lines in the flow table. But instead of using ordering and priority, we're actually just using a negation. All those packets that don't match the destination IP that's going to be transformed, they just get passed through. Here, that and sign is actually just sugar for sequential composition. So you have one match, sequentially composed with another match, is logically ending them. Likewise, parallel composition turns out to be OR. Now, packets unchanged, as I mentioned, which is something we couldn't express in the previous program in Openflow alone. What about routing? Well, same deal here, except note, we really don't care about the ordering. Parallel composition is order independent, so we could decide to put our not match case up at the top. What about monitoring? Oh, it's just declaring a count bucket. And we want to compose all these different pieces of functionality together in a prescribed fashion. So we want to balance, then forward, and at the same time, monitor. Well, that's all we need to write. And this is something which the programmer can write down once, and it doesn't matter how complex any of these functions are internally, what they're built up of in terms of primitive functions on their combinators, nor how they might change in the future, which compared to what you have to do in Openflow is very different. This table, totally new table you have to write to combine the previous tables we saw before with the logic specified on the previous slide. You'll have to take my word that it's correct. I'll have to take my word that it's correct because I haven't formally proven it to be, but I believe it is. But you have to write this totally new table. It's going to be geometrically larger in size. And hint at what makes dynamics hard with Openflow, anytime you change any of those other individually precursor functions, you're going to have to rewrite this whole thing, which is a huge mess. So this better interface that we're providing does require something. Namely, it requires a more sophisticated runtime to be able to support its abstractions. Not enough time today to really dig into it, but to give you a little bit of a flavor, I had mentioned interpretation and compilation before. So what exactly is interpretation? Interpretation is when we have packets that end up getting sent to the controller for whatever reason. Maybe it hasn't been able to compile and push the rules down to the switch in time before a packet actually arrived. Maybe there's not enough space on the rule table, or maybe this packet has some kind of specialized logic that requires it to be sent. So we'll take our function and we'll evaluate it on that packet when it comes into the controller. That's interpretation. Compilation is to analyze the function and figure out how to efficiently turn it into a rule table, which is going to require implicitly doing a lot of the logic and automating that logic that the programmer would have had to manually do in the previous slide, and then push that on to the switches. So the rules that basically make that function are on the data plane. OK, so little systems architecture. We've got our Openflow switch. There are all sorts of messages, stats requests, packet ins, flow modifications, errors, what have you. So a runtime is going to have a thin layer, which is going to take Openflow messages in, push Openflow messages out. It's going to interact with a couple of components above it. The modules that I'm highlighting today are the topology module, because we have located packets, an interpreter and a compiler to do interpretation and compilation. And these are going to be linked in terms of their behavior. I'll show an example about that in a moment. And an engine for our buckets. So on top of this, the program runs. And let's look at one particular program. So if match a field equal to a value, I'm holding these abstract for right now, we'll forward out port 1. Otherwise, we'll go into this forward bucket B, and at the same time, we will forward out port 2. What's going to happen? Well, the compilation pipeline is going to take this function, and it's going to turn it over several stages into a table that can go out to the switch or switches for which it's applicable, and push those out to the switch. So that way, when a packet comes in, here a packet where field F doesn't equal V, packet will go through, match on the rule, and if you notice, we've got a rule saying forward 2, so We do the forwarding to in the data plane, fast, don't hold up anything in the network where we don't have to. Then we'll modify the packet and forward it again to the controller. So now we have a packet in the OF backend, which came in port 1. It's been tagged. And it was also tagged with the modification we made, which was to put a little bucket, flip a bit saying that this belongs to a bucket, which then lets us, when it goes into the interpreter, evaluate it against our policy, but realize none of the forwarding actions in the data plane are significant any longer. So we produce only one output packet B that goes into our bucket, and we've completed the interpretation phase of this. Now note, we might not have had time to install those rules or been able to install those rules for whatever reason on the data plane, in which case the packet would not have been tagged before going to the controller, and thus the interpreter would have actually gone through the full process of generating a second output packet and forwarding it. So the abstractions I've covered for modularity thus far, or the abstractions we provide in the work, rather. On the interface, these primitive functions and the operators that combine them, so total interface redesign. And in the runtime, I've shown you a little bit about linked interpretation and compilation, though there's a lot more to say. I've pretty much skipped over the compilation process, but I'm happy to tell you about it afterwards. It involves something called classifiers and taking cross products with shadowing. And the last runtime abstraction or concept that we've covered is that of controller buckets. So we can now move on to dynamics. And dynamics, again, are when the controller's output and internal state are going to be changing over time. So it turns out this has the same types of difficulties, or the same form of difficulties as previously. There are ones that are intrinsic, such as, well, this is mission-critical software. It needs to work right. It needs to be clearly structured for maintenance, all that sort of thing. So how do we structure this correctly? Can we verify properties about it? Can we make it run efficiently in terms of how it interacts with the data plane? These are all inherently tricky things. And then we've got the exacerbation of the bad interface Openflow. As I said before, if you have multiple tables, you change one, you have to rewrite the whole combined table, some other stuff. But we've gotten rid of Openflow as our interface, so I won't dwell on that. Instead, we'll just jump right in so I can tell you about how a Mac learner works. This is that canonical SDN application, which I mentioned before, for doing dynamics, showing how dynamics can be made to work. So what does a Mac learner do? Well, we've got this plug-and-play network. We've got a bunch of switches. They don't know where the other switches are or how many links their neighbors have. They just know what links they have. They don't know who the hosts are yet or where the hosts are located in the network. They need to figure this all out, and it's a very naturally distributed piece of logic. Each switch is going to figure this out independently by first flooding packets. So that way we know that if I put a packet in over here, it'll flow through the network and get to you. But that's a very inefficient use of network resources. So over time, each switch is going to observe the packets that go through the network. And as it observes them, figure out what the shortest path back to the host that was sending is, and thus start unicasting. And again, this is sort of the canonical application you'll see in SDN tutorials because of its simple dynamics, but its sort of robust usage of features. Let's look at this a little more precisely. We've got our switch over here again. We have a packet that comes in, coming from the orange host and going to our brown host. So it goes into the switch, and the switch, by default, is going to flood the packets out, which is great. But if we're, say, an omniscient observer, or the switch observing what's happening, the switch has learned something, namely that packets are coming from the orange host on port 1, which means that orange host is downstream of port 1. So we can install a rule on the table, at least conceptually, saying, hey, packets destined to the orange host should get ported out of port 1. Likewise, so we get a return packet. And now we're going to unicast. Sorry, I moved through that animation a little quickly. So we unicast out. Plus, we learned something new, namely where the brown host is. Brown host is downstream of node 3, so packets destined to brown host from now on can be unicast out port 3. That's the way Mac learner works. Any questions about this logic? Does it seem relatively simple? You can nod your head or... OK, I'm assuming that's... Sure, excellent.
So, okay, you learn basically when the packets arrive, but and you do it by sending the packet to the switch, to the controller figures out and then installs the rule. How do you forget about ports and source addresses?
You mean on the controller? Like monitoring them? Okay, so that's a question I would love to answer, but at the end of the talk, or offline time allowing, I'll give you a very quick answer right now. It involves basically a dynamic function like the one I'm about to show you, but a dynamic function that involves just filters and multiple buckets. So you're going to set up some derived packet function that is doing in parallel multiple buckets, each preceded by a particular filter, and then as time passes, you're going to remove some of these expressions from it, thus reducing packets getting sent. And that's going to use the machinery that I'm about to introduce. So in the first abstraction we use for doing this kind of dynamics are simply dynamic packet functions whose value can change over time. These are essentially wrapped in a class in Python. So we basically create a new dynamic function, in this case MacLearner, that's going to be initialized. First, we're going to create a bucket. In this case, it's this packets bucket, which is actually a library we have that provides just what I mentioned to you before. So we'll only see the first packet for each switch and source MAC pair. And then we're going to register an update function, defined momentarily with that. And we'll initialize our function to, well, flood and run our query in parallel. Great. So how does update work? Well, update's going to take a packet that went into the bucket. And what's it going to do? It's going to change the packet function, its current value, self.packetFunction, PF, to an if statement, which is another derived statement involving parallel and sequential composition and negation. Basically, if we're matching, we're destined to the MAC that we're just learning, then we're going to get forwarded out the port that the packet we learned on had come in, the downstream port. Otherwise, we're going to continue doing exactly what we had done before. And this is essentially all the code you need to do Mac learning in Pyretic compared to that old slide you saw before with POX. And this is with the sort of first of our abstractions. But we've got more because there are problems with this. First problem, well, look at the update syntax over here. It turns out this is a pretty common idiom. So set the packet function's current value of a dynamic packet function to be, if a special condition, then some special action, otherwise the normal action as before. And the problem with this is that what we're doing with this update, we're expressing it in a mixture of our DSL and general Python, which is kind of ugly and creates some problems with deeply nested if statements that can even affect interpretation. But fundamentally, the more important part is that it doesn't provide the runtime any information. The runtime just sees the packet function was changed, but it doesn't really know how unless it starts to try to analyze arbitrary Python code, which is Turing complete. So not a good way to go. How do we solve this? Oh, and why does the runtime want to know that this is a partial change? Well, because it turns out you can do some very clever things, like cascading recompilation, which I won't have time to talk about today, but we can chat about it after if you'd like. So Kinetic, our work on dynamics, introduces an abstraction into Pyretic that actually goes into the runtime, namely a new operator, update. So we're going to have a packet function. We're going to update it with a delta, which is just a filter packet function and a normal packet function. And this semantically is going to be equivalent exactly to that mixed Python Pyretic DSL before. But not only is it nice and crisper, it's going to provide that needed information. So now the runtime knows and can run optimizations that have been implemented in it. So we've got our old update logic, and now we can clean it up a little bit with the delta. But as you'll notice, we're kind of mixing and matching source and destination IPs. It's a little ad hoc. More fundamentally, it's also hard to look at this and say, OK, well, what will this thing do in the future? Which is where our second and bigger abstraction in the kinetic work comes in, that of Fsm Dynamics. And so the idea here is that we're going to make a packet function which is encoded using a finite state machine. So this finite state machine is going to have states, each one of which maps to some packet function in Pyretic extended with the delta update operator. For example, our first initial state might be pass packets on through until a warning event comes in, triggering an exogenous, externally created transition to a new state in which we're dropping packets. Something's gone wrong, we're going to drop. Later on, we get the all clear. We'll go back to our initial state identity and begin forwarding packets through once again. What's really neat about that, so that structure is going to be useful later on for doing things like verification that I'll show you during the evaluation section. But what's really neat is that when you take these finite state machine encodings of packet functions and you apply parallel or sequential composition to them, what you've actually done is implicitly code an exponentially larger product automaton, where each crossed state in the product automaton is just the packet function from the first crossing state composed with the packet function from the second crossing state. So you could see that in parallel composition. You're just changing the composition operator. And as I said, exponentially smaller in the number of states and the number of transitions. So we can get these really crisp, compact encodings using a linear number of compact FSMs combined using just parallel and sequential composition. And this is something we'll exploit shortly. So before I go to exploiting that property, let me show you how we do an FSM Mac learner. So this is going to be specifically for one particular host and for the particular switch over here, the orange switch. We start an initial state with 3 variables. 1, a port, just a number. That starts off to be 0, because we don't know what port we're forwarding out. 2, a packet function, PF, which corresponds to that port. In this case, we don't know which port, so we're going to flood. And 3, a topology change variable, TC. So packet comes in, and it gets flooded out according to the policy. But this also generates an event that's going to say, hey, port value n, in this case 1. So we're going to update our port to 1 and our flood to forward at port 1. And we're going to stay that way. Oh, and of course, the runtime will then install the right rules, because we're building this as a library on top of Pyretic. So we'll keep doing that behavior until, say, a link fails, in which case it doesn't make sense to keep doing this, which is also going to create a new event, topology change. So we're going to turn TC to true. And because several other variables depend on TC, this is going to create a cascade of endogenous transitions back to the initial state. OK, limited time, so I'm going to flip through this rest quickly. So conceptually, we had that for the orange FSM. We'll need 1 copy of these FSMs per host. But if we don't know this a priori, we might run into some problems. So what those problems will be, I'll tell you in a sec. But first, this concept of basically taking 1 FSM per set of related packets, we formalize as a notion of a located packet equivalence class. This is the largest set of packets that are all going to be treated by the same FSM copy. And in this case, that set of packets might be match on the switch that we saw before, and the desk map being orange. And Pyretic filters provide a great way of doing this. They're basically just sets. We have the programmer provide a projection function, which is going to map each packet to its equivalence class. So in this case, the equivalence class is going to be the one that matches all packets that have the same destination MAC address at that particular switch. So how do we implement this thing? Well, we got the programmer that provides the finite state machine and this projection map. And now we're going to create 1 FSM copy for each one of our equivalence classes. They're going to be n equivalence classes. We're going to run them all in parallel. And we're going to restrict each using just the filter, the equivalence class filter and sequential composition, to its set of packets. And there's some event handling stuff. I'll just skip this. You can ask me about it later. But the really critical thing is, well, we've done an exponentially smaller encoding here. So the number of states of the FSM is S. We had n FSMs. Well, we're going from S to the n states that we have to keep alive in our runtime to S times n states. Much, much more compact. Question?
Why is that
important? As in, it sounds very neat in terms of a formula, right, theoretically.
Sure.
But this resides on the controller, sure, as in for most, is there evidence that the number of states when you're doing Mac learning for reasonable sized networks is going to be a problem?
Oh, so that's a question we should get into more a little bit later. But what I'll say right now, because of time constraints, is without the next trick, yes, it becomes a serious problem because a priori, and if this is MAC addresses and we don't know the MAC address space beforehand that we might be operating on, you're looking at 2 to the 48 being the value of n. Even if S is 2, 2 to 2 to the 48 is an impossibly large number for any piece of computational machinery, I think, to maintain realistically.
The other question that I'm struggling with is Mac learning seems like a very poor example because Mac learning is one of those rare things that networks can automatically do very well without any configuration. As in, I know it's not your fault. I know everybody in SDN uses this example. Yeah. It's the worst example ever because it's, as you said, Ethernet is plug and play, and it's actually one of the things that networks do well. So it sort of takes away from the actual work, but anyway.
Yeah, well, so my quick answer to that is it is the canonical one in this area, and it's very good for illustrative purposes. You'll have to take it on faith that this can apply to lots of other things. We can talk more about that offline because I just don't have time left to address it more thoroughly right now. So we've got this tremendous reduction, but we're still in a very large state. So we've got 2 to the 48 if we're doing MAC addresses. So we need to get that smaller. But it turns out we're in luck. Each of our FSM copies is a copy of the same spec, which means that all of them start in the same initial state, which has the same initial packet function. So we can just return as our policy that initial packet function delta'd, so using our previous machinery, only by those FSMs that have changed since we started running our program. Or, even more efficiently, by those FSMs that have changed and not returned to the initial state. Oh, and that pun was intended. OK, so abstractions and dynamics. Interface, so we've got these dynamic packet functions, this delta update, and these FSM very compact encodings that can be verified, as I'll show you in a moment. The runtime, I haven't covered update staging. I haven't covered cascading recompilation, but there are things we have in there that are really neat. And I did show you how we can do this on-demand product automata expansion. So now let me go through our concluding remarks in like 2 minutes. OK. So bottom line, we get comparable performance to other Openflow-centric platforms from applications we took out of the wild and made best apples-to-apples comparisons we could in terms of latency and throughput. And that's without many of the optimizations that I've spoken about you today, several of which are still in progress or weren't at the time we ran these experiments. We get a far more compact set of programs that are also, you'll have to take my word for it, easier to read. Example, a server load balancer with 24 lines instead of 144 in POX and almost 1,000 in Floodlight. We wrote a stateful firewall, which is actually another example where you're going to get a very large expansion, potentially, because you're running the stateful firewall logic for each pair of hosts, where one host is on the inside, one on the outside, of which there can be many, many pairs running in parallel. So that's actually a concrete example application where you will want to use the tricks I just showed you. And we couldn't find any programs out there in the wild that did this type of dynamics. I'm going to guess probably because it's very hard to write. Yes?
Is it simulation or re-implementation? What is the setup?
So these code lines are just, this is just the code. In terms of the experiments before, these were experiments run on Mininet, not on a real network. We didn't have access to a test bed large enough to really do it with our deadline. But that's our next step. We're planning on doing this. So, oh yeah, last point in the evaluation I want to make, dynamics are verifiable. So we can actually write properties in computational tree logic or other temporal logics to say things about the FSM-based functions. So for example, we can do something like convergence on all future execution paths in every single future or current execution state on any of those paths. If the port's currently 0, which means that we're flooding, then there exists at least a path where there's a future state in which we're not flooding. So we can always converge, is what this property says. And we can make stronger statements by tweaking our model slightly. We can also say things like stability. So for all execution paths, for every single execution path, if we're unicasting to a particular port, then for every future execution path, we will continue unicasting until there is a topology change. Today's talk based on 2 pieces of work, one Pyretic and a second one Kinetic, just in submission. Great collaborators. I'm happy to tell you all about them and which pieces of the work. Most of what I presented today, I've tried to focus on those things which were more my core contributions, but there are a couple of things which other people really helped out with. We don't need this. We can talk about it later. Future work, you can probably guess there's a lot of different things, and look at this slide for just about 1 more second. And I'll just finish off with quick mention of my past work on the network to improving host side, my work on accelerating virtual machine storage, basically streaming virtual machines from storage images in a scalable manner. This was at Conext in 2012 and did spin off that neat startup, Infinio. A little bit more previous, excellent institution. I interned at Microsoft Research, and we did this project on improving end host efficiency. Love to tell you more about that. It was published in Usenix ATC, and it's actually percolated out many generations later into product, I think Server Center 2008. From the host to the network side, I've actually looked mostly at how wireless interfaces can be used to enhance the capacity or range of the network, so maintaining the connectivity of mobile mesh networks. Won a Best Demo Award at MobiCom, MobiHawk, and also was presented as a full paper at Conext. I did that work at Columbia, and lastly, some older work I did at Technicolor while interning there on using opportunistic mobile contacts to disseminate videos in optimal ways that accounted for the impatience of human users. And this resulted in a couple of patents. And I'm done. I'm going to leave that slide for you to stare at, assuming there's any time for us to stay in the room.